Hello, this is Alan Leonard, and I'm going over my explanations for my answers for assignment 2. For problem 1, part 1, I was asking about how to explain web caching and how to improve website performances, reduce network congestion, discuss the trade-offs between link speed and deploying cache solutions, and which one I would try to prioritize for the question given. I talked about how web caching helps performance and efficiency by storing content already downloaded or found in much closer places and like servers closer to the users instead of having to download it again and creating completely new connections across the web. Caching is definitely higher on the priority for the question we had for using a large-scale web service that serves millions of users globally, since this would allow us to locate different information much closer to users, as I've had to create connections across the globe so many times over. It would also help reduce stress over repeated data connections and help reduce bandwidth. For question number 2, compare HTTP 1 and HTTP 2, and I talked about the improvements that were all added with 2.0 instead of 1.1, which allowing multiplexing, UCP, using push to give resources before they even asked for cross-connect on gets statements, using HPAC for compression instead of doing them all themselves, and just better optimization overall. SMTP, IMAP, and HTTP email services all varying what they did, with SMTP pushing messages from client to servers, IMAP allowing to receive messages from servers and also creating stable connections across the servers. But HTTP was the best overall, as it was compressing all the data, lower traffic, bandwidth usage, and didn't even have to use dedicated email clients by comparison, when the other two almost have to work together for it. For question part 3 of it, I described the DNS resolution process and scalability challenges of centralized DNS versus hierarchical. DNS has a few steps when getting an IP address. I talked about how there's the recursive version where resolver sends a query to DNS, tries to see if it has the info on the specific server that was accessed, then decides to either, if it has the info, sends it back, or if it doesn't, repeats this by going to another DNS server and going through them all until it eventually finds it, and once it does find it, it eventually sends it back to the original user. The two other ways, the iterative, and then there is also using caches. Iterative uses authoritative DNS service in order to basically search through any other ways it can find and find the exact IP address for it, or otherwise it uses caches in order to try to find the best root server answer that it can create based on the information that is given, if it can't find the exact thing when it's wanting. Central DNS, though, models have a few challenges being done on huger scales, one being the distance it increases over time as servers grow, and the second one being the bottleneck that'll happen if a huge outage goes down, almost everything is cut off. And the reason the hierarchical structure would help to mitigate all these issues is it would allow a sort of like split a connection across them all. And so if something happens in outaging on one side, it only cuts off that section instead of everything else with it. It also allows to cut down on distance, as instead of going all the way back to the very beginning, it has a sort of tree that goes down. Instead of going all the way up to the top, it only has to go certain ways to the other points and nodes across it from different branches. For problem 2, imagine you're responsible for high performance. Discussing TCP and UDP, I discussed both, with UDP being much better for the real-time connections that we're trying to do in this problem of having a new real-time communication application. UDP has a larger range of networks, can share information much quicker, and also do all of this in real time with only a few faults, while TCP slower, less bandwidth, more prone to bigger problems across it, and also resource heavy. This would also go to connection-oriented solutions just not being as fast like TCP, as they much more resources, and even though there's a stable connection across it, with them having some issues on UDP, UDP is still able to make up for that with just being able to run them again and everything. With also having much more connections squished down into one instead of like TCP not being able to multiplex and everything. For number 2, describing multiplexing, deep multiplexing. Multiplexing works by adding up a bunch of different connections all into one and then running it across as like a package, while demultiplexing takes it, decodes it, and then sends each one to their own address that they're needed to go to. The difference between demultiplexing on UDP and demultiplexing on TCP matters hugely, because UDP is much faster and has some unorganized sets of information when it's all set across, while TCP is much slower, but it's all ordered correctly and has a lot less having to deorganize all of that, or I say reorganize all of it when connected through. And although ordered would help early on with being like this message was first and this one sort of thing back and forth across, UDP was just better in general because it gets the messages directly across, so we could use the same lines for multiple people talking and it would still be organized straight to them, instead of being this person message first to this person message after that and this person message, so it goes one by one. It would be much quicker, streamlined across it. And for number 3, describe how to stop and wait and with automatic repeat protocols help ensure reliable data transmission. RDT 2.0 waits for responses back. After they send a message, they wait to get a response back before they keep going, while ARQ sends multiple requests and repeats it in order to make sure it gets the same thing across for both times. Both of these help just maintain that the packets receive the right thing. There was no losses, duplicates, corruptions, as it gets multiple of them and makes sure that they're across. And like RDT2 does not keep going if it doesn't receive that back. Well, our ARQ will keep going until it makes sure that it has the right response back, which is why it repeats. Checksums are used for packet loss by finding corruptions and defects. Sequence ordering ensures all packets received are found in the correct order, and lets repeats to be found or missing packets in the order. Timers and retransmissions are also very important, as it makes sure packets aren't lost in the ACKs or the NAKs, because of the corruptions that can happen with that. And there are more features and designs that go on with this. Problem 3, we are going through sequences. I found 118 to be the time segment for segment 1, as we start at 118. And as they each going, it's increased by the first five segments each contain 506 bits. Delay between the sender and receiver is 7 time units. So the first segment is at T8 for when it's receiving. So segment 1 is time segment since 118, then 624 for segment 2, 1130 as it adds up across it, down to 2142 for segment 5. This being added on to the 8, 9, 10, 11, 12 across, but they're also, because of the missing packets we've given, only 3 of our receivers end up getting what they're looking for, as I keep sending back ACK field values trying to receive the next ones until 12 eventually gets through afterwards, and it's still looking for that request back. Alright, I think that is the gist of everything. Thank you.